All right, so we'll come back. Let's get started. Looks like the attendance is slowly dropping. I'm probably sending the wrong message by putting the videos on YouTube. Is anybody looking at them? Maybe the fact that you can look at them at any time is sufficient. So today I want to cover unconstrained rigid body dynamics. I hope I sufficiently confused you the last time about Quaternions and rotations and so on. And today we will look how we can simulate the rigid body until it starts colliding. And then the next lecture will be about how to deal with collisions and contact of multiple rigid bodies. Again, this is a pretty standard topic. There are lots of physics engines which implement this type of stuff. It's like Havoc, Bullet, ODE, and so on. There are specialized engines for 2D, like Box 2D, and we will cover the basic principles how these things work. It's also like the basic for robotics, because in robotics, the basic model is essentially a bunch of rigid bodies connected by some joints. That's really what a robot is, right? And to a first order approximation, that's also what a human body is. It's just like a skeleton, which is like a bunch of bones connected by some joints, by some constraints. Okay, so oh yeah, and what I meant by this is that we are again following the David Barraff's course notes on rigid body simulation. Even though some things I think I know how to derive in a little bit cleaner way. So something I will do a little bit differently. So the first thing we need to realize is that we can have the body space coordinates and world space coordinates. So if I have some rigid object to be simulated, that's really similar like when we are doing finite element methods. We were also talking about some object in some local object coordinates, right? So there is some origin of my coordinate system, and here are local coordinates x, y, z. So this is my object before it starts moving, and then when it starts moving, then there is some reference coordinate system of world coordinates, and that's where the object will eventually be living. Same object living in the world space. So let me put it here, object space. Whoops. Object space, world space. And what we are concerned here about is about the motion of the object in the world space, right? So the object, we can imagine the rigid body is a collection of particles, infinitely many particles, but we can just think about it as finitely many particles. You don't see me? That better? So if I have one particle here, I can call it P. Let me see what the right notation is. I think P0I, where I means the index of the particle and 0 means it's in the object space. So that's really just a vector for one particle. And you could imagine I could sample the rigid body with some particles. And every particle can also be associated with mass. Again, if you imagine, maybe you could imagine those are like atoms of your object or something like that, whatever you want to think about. And so every particle has not just a position, but also some mass. So the mass would be mi, mass of particle I. So the first thing we can compute is center of mass, COM, which you could probably tell me how to compute a center of mass, right? That's very simple. So it's sum over all particles, mass of the particle and the position vector of my particle divided by the total mass, capital M, where the total mass means sum all of the individual particle masses together. Very simple, right? So without loss of generality, we can assume that I chose this coordinate frame for the object space such that the center of mass will give me 0. So without loss of generality, we can assume that the center of mass is at 0. because I can choose the coordinate frame in the object space whatever way I want, so I can as well put the origin to coincide with the center of mass, right? Why not? That actually simplifies things, because lots of these things, lots of quantities will be expressed with respect to the center of mass, okay? Now, the last time we established that rigid body has 6 degrees of freedom, right? And those split into the translational ones and rotational ones. So translation, I will denote as xt, and that's a 3D vector specifying the position of the center of mass at time t. So now we are in world coordinates. We assume this rigid body is traveling through space. It's doing some motion. And this vector xt gives me the position of the center of mass at time t, and t is my simulation time as usual, right? We will eventually be discretizing the time and doing some time stepping and so on, but that's not important yet. And the rotation can be represented, for example, by rotation matrix, which is a matrix from SO3. So this is a translation, and RT is a rotation, which has, those are the first 3 degrees of freedom, those are the second 3 degrees of freedom, altogether summing to 9 degrees of freedom. It's good to have like an intuitive understanding of what actually is in this rotation matrix, right? Because if I write the rotation matrix like this, like RXX, RXY, RXZ, RYX, RYY, RYZ, and RZX, RZY, and RZZ. I can also write it more succinctly as Rx vector, Ry vector, and Rz vector. And can you tell me what is the geometric intuitive interpretation of these Rx, Ry, and Rz column vectors? Exactly, yes. So those are, so if these are my body space axes, the x, y, and z are my body space axes, then in the world space, the body is, the coordinate frame is somewhere else, right? It's doing something like this. And this will be my Rx, this will be my Ry, and this will be my Rz, right? So I can also look at it as telling me where these standard basis vectors map, because r times 1, 0, 0 is Rx, right? Of course, r times 0, 1, 0 is Ry, and so on. And that tells me exactly what are the coordinates of my axis in the world space after the rotation. That's very basic thing, but it's good to keep it in mind. Okay. So now let's take a look at velocity of a point. So we assume this rigid body is moving in the world space somehow. There is some trajectory parameterized by this time t. So let's compute velocity of this point for the given trajectory of a rigid body. So assume somebody gave you the trajectory and you want to compute the velocity of a given point. So we are looking at this point number I. So how do we do that? So, the derivative in this context or in these notes is usually denoted as a dot. Have you seen this notation before? So by this, okay, so what I mean by this notation, by PT, I mean coordinates of this point in the world space, parameterized by t. So the p0 meant the point in the object space, and if it's without an index, then I mean it's the point. That would be my pi, or just p if I don't need to index it. And by the dot, okay, so by the dot I mean differentiation with respect to time. Is that everybody familiar with this notation? Because I could also be writing like this, right? But there is like a lot of writing, so people just abbreviate it as p dot t. So this is the same thing. Okay, so what is the derivative of a point on a moving object? Well, maybe I should start by writing what is the position, right? That's sort of simple. So I take the rotation at time t. I take my rest pose coordinate p0, and I take the position of the center of mass, xt. So because the body is moving, that means the center of mass is moving. That's what this trajectory x describes. And the rotations are also changing in time. That's the RT thing. Everybody okay with that? Cool. So then it's sort of easy to differentiate. So the time derivative of pt, well, what that will be? Well, simply differentiating r, whatever that means. P0 is constant, right? This point in the object space is fixed, plus the derivative of the trajectory of the center of mass. So first, this thing, the xt, that's simple, right? Because that is just velocity, specifically velocity of the center of mass. Sometimes it's called also linear velocity, to differentiate it from angular velocity. And the angular velocity is essentially this derivative of the rotation matrix. That's basically something that leads to angular velocity. And while the linear velocity, that's simple, right? That's just a 3D trajectory being differentiated. With the rotations are always the troublemaker, right? So here we also need to be a little bit careful how to deal with the angular velocity. Because what is the derivative of r? R is a 3x3 matrix, right? It's a 3x3 matrix. So the derivative of that will also be a 3x3 matrix, right? On the other hand, you know from physics that angular velocity is a vector, right? So what is the connection between the two? We need to discover how, from the differentiation of the rotation matrix, we can get to the angular velocity vector. And the thing is, the interesting thing is that this derivative of rotation is a 3x3 matrix, but it's not a general 3x3 matrix. It's a very special type of 3x3 matrix. Does anybody has a guess what type of 3x3 matrix this R dot is? That is not simple. So let's take let's take a look at it. So we know that RT is a rotation, right? Let me drop the subscript t to make the equations a little less messy. We will just remember that R depends on t, it's a trajectory. And because it's a rotation, then we know that RTR, you know what, I will do this on a separate paper. This might be more writing. So we know because R is a rotation, then certainly RTR is identity, right? We know that. So we can differentiate this entire expression. So we can differentiate RTR. That must be equivalent to differential of identity, right? But identity is a constant. So if I differentiate the constant, I will get 0, right? 0 meaning a 3x3 matrix full of zeros, right? I've been talking about this differentiating matrices before, so I'm not gonna do the same discussion again. But you remember that differentiating a product observes the standard product rule, right? So the differential of RTR with respect to time, of course, equals, well, the differential of wait, sorry, I did the wrong notation. Differential of RTR is the differential of RT times R plus RT times the differential of R. So if I stick with this transpose, doesn't matter if I first differentiate and then transpose, because transpose is just reordering the elements, right? So it doesn't make a difference. And if I go back to the dot notation, which is usually used in this context, then this is the differential of R transposed R plus R transposed the differential of R. And this says that this thing must be 0, right? So what that means is that the RTR dot plus R dot transpose R, I just swap the order, doesn't matter, is 0, right? So what that means is that RTR dot equals minus R dot transpose R, which, and then look what I can do with this. This is nothing but RTR dot the whole thing transposed, right? Because what is this? R dot transpose R. So if I transpose this thing, I will get R dot transpose and R, right? Because of because of this rule, AB transpose equals B transpose A transpose. But see, this is the same thing as this, right? So what does that mean for the matrix RTR dot? There's a name for such a matrix. So the matrix is equal, or minus of the matrix is equal to its transpose, right? So if I write it in general, minus of the matrix is the matrix transpose, right? How is this property called? Anybody remembers linear algebra? Huh? Almost. Symmetric is if there is plus, right? Huh? It's anti-symmetric or skew symmetric, right? So what this means is that R, and I will explain what that means in a second if you haven't heard it before. That means that R transpose R dot is skew symmetric matrix. Which means exactly this. If I transpose it, I can just get the same matrix times minus 1. That's what skew symmetric means. And in a 3x3 case, that means that I can write the skew symmetric matrix like this, right? So first thing we need to realize, if the transpose gives me the matrix negated, then on the diagonal there must be zeros, right? Because if I transpose it, the diagonal doesn't go anywhere, so times minus 1, the only number that has this property is 0. And there are some numbers here. I will call them omega 0 z for reasons that will soon become obvious. Omega 0 z. So this needs to be the opposite numbers, right? This might be minus something, it might be plus the same thing, or the other way around. I could put the minus here. Now you will see soon why I'm picking this particular convention and why I'm calling it omega. So here I have minus omega y0, and here I have plus omega x0, right? So this is a perfectly valid 3x3x3 matrix, which is skew symmetric, right? And this is the general form of a 3x3 skew symmetric matrix. So how many degrees of freedom has a general skew symmetric matrix, 3x3 skew symmetric matrix has? How many independent numbers are there? Just 3, yes, yes, yes. And that's basically how is angular velocity born, right? Because I can write this matrix as, oh, maybe I should have used different bracket here. This is like an operator. Okay, I'll explain that. So if I say that omega 0 is a 3D vector containing omega 0x, omega 0y, and omega 0z, which is just a 3D vector, then I say that this square bracket operation converts this 3D vector into this skew symmetric 3x3 matrix. Okay, so this omega 0, where the square brackets are now an operator which takes a vector and produces a 3x3 skew symmetric matrix, is a 3x3 matrix which is sometimes called a lowercase SO3. I don't know if you heard about, so this is, here we had the uppercase SO3, right? This was the Lie group of rotations. And the lowercase SO3 is the Lie algebra corresponding to the Lie group uppercase SO3. Okay, if you don't know the basics of group theory, then just ignore that. It's not that important. Everybody okay with that? So what is important here is that this matrix, this skew symmetric matrix, is essentially performing cross-product operation, right? In the sense that if I have, okay, let's do it in general. If I have some 3D vector A, and I create a 3x3 skew symmetric matrix from the vector A like this by doing the square bracket operator, then I get a 3x3 matrix, right? If I multiply it with B, what do I get? B is a 3x1 vector. And you can guess. I sort of said it already, right? So, I get a 3x1 vector, and that 3x1 vector will be nothing but A cross product B. And that's also why I define the minuses in this funny way, because if you write it all out, if you like write it out like this, so 0 minus AZ, AY, AZ 0 minus AX minus AY, AX 0. And if I now multiply it by BX, BY, BZ, then you will get this, right? You will get minus BY AZ plus AY BZ, and so on. Oh, not just 2 here, really, not another third one. And this is exactly the same as cross product. So that's sort of interesting. Here you can start seeing the relationship between the derivative of a rotation matrix and the angular velocity vector, because this omega 0 is going to be exactly the angular velocity of the object in the object space. So let me write this again. So what we've shown here is that RT R dot is this matrix. Oops. RT R dot is this matrix, the skew symmetric matrix born from some vector omega 0. Well, that also means that I can write the R dot, if I am interested just in the pure derivative of the rotation matrix. Well, that's just R times omega 0, right? Because I just multiply this equation from the left with R, and RT is identity, so that goes away. Okay. And now, so remember what did I start with? I wanted to find a nice formula for the derivative of a point attached to the rigid body, right? So let's return to that. So the formula was P dot equals R dot P0 plus X dot, where the X dot is the linear velocity. And if I substitute here this expression for R dot, then I will get that this is R omega 0 P0 plus, you know what, let me call this V, this linear, because the X dot we can denote it as V, that's the linear velocity, the velocity of the center of mass. And using the cross product formula, I can write this as R times omega 0 cross product P0 plus V. So that's expression of the angular velocity in the body coordinates here in the object space. So if the body is rotating somewhere, moving around, it's translating and rotating, right? That's all that rigid body motion is. So the axis of rotation in object space, that would be my omega 0. And how can I compute it? Like this. Now, a more useful form is to express the axis of rotation in the world space. And how can we do that? We can do that using a simple trick. If I write this again, P dot is R omega 0 P0 plus V. So I just copied this part of the equation, and see what I can do here. I can stick in here RTR. That's identity, right? I can certainly multiply it with that without changing anything. And I will get R omega 0 R transposed R P0 plus V. Okay. So now let's take a look at this matrix. What is this matrix? R omega 0 RT. Does somebody has a guess what this matrix will be? Well, the first thing we can realize that is also a skew symmetric matrix, right? Because if I take this and transpose it, what will I get? Well, again, so I will get R, that's this guy transposes R, then I will transpose my omega 0 matrix, the cross product matrix, and again RT, right? The omega 0 was a skew symmetric matrix, so its transpose is equivalent to just multiplying by -1. So this is R omega 0 R transpose, okay? So that means this matrix R omega 0 cross product RT is also a skew symmetric matrix, right? So that means that this whole thing R omega 0 RT can be written as one cross product matrix from omega, a different omega, right? Good. So that means that I can write this entire thing, so I can just plug it in here, and I just write the omega thing here, RP0 plus V. And if I denote the RP0 as P, because the P0 was the rest pose, the object space or rest pose coordinate of my point. So if I rotate it, if I denote the rotated point as P, then I can just write that this is, oops, sorry about this. See that? It's a little cramped in there, but I will manage. This is omega P plus V. And because this is a cross product matrix, and this is nothing but omega cross product P plus V. And this is the most basic formula you have probably seen before somewhere in physics. I would guess, I would hope. Where this omega is the angular velocity in the world space, the actual world space vector, which corresponds to the instantaneous angular velocity axis. P is the world space coordinates of my point which I'm looking at. So this really, you can imagine the picture where you have like an axis, a point, and the cross product shows you the tangent vector as the point is rotating on a circle around this axis. Okay, so yeah, what is good to remember is that it really matters in what coordinate system do I represent the angular velocity, and that the conversion between them is really just like this RRT sandwiching type of thing. Okay, so this is, by the way, this whole thing can be done also in Quaternions, which I'm not gonna do the entire derivation again in Quaternions. I could, but I guess you would get really bored because it would essentially be the same thing. Let me just skip to the conclusion of that derivation. So I guess in Quaternions you could write the trajectory of a point like this, right? You could say that P is Q, P0, Q conjugate, if Q is a unit Quaternion, plus V. So the linear component stays the same, and this is the Quaternion sandwiching product which realizes rotation, right? Then I could be massaging this thing, then I could be differentiating this thing as I was before, and what I would end up with eventually is that the derivative of the quaternion is 1/2 omega q. So this corresponds to the derivative of a rotation matrix. This is like an analogous result to this one, omega r. That's what we had somewhere. Where did we have that? Maybe I didn't really derive it, but we can derive that derivative quickly. We had this one, that r dot equals r omega 0, right? Then I can say that r dot equals, let's let's see if I will get the right thing. Omega 0 RT R, where this thing is my omega thing. So this obviously is, oh, wait, sorry, I'm out of the picture. So this is omega R, which is what I've shown here. So, okay, let me do that again because I by mistake did it outside of the camera. So I started from this. So this is only converting in from the body frame, body coordinates to world coordinates. So I put here RTR, which is identity. Then this thing is the cross product matrix from omega, and this becomes omega R, right? So that's this. So my point is that with quaternions, I get almost the same thing. The one slight difference is what do I mean by this omega? What do you think I mean by this omega? What do you think I mean by this invisible operation here? That's the easy question. So here it's matrix product, right? What product here? What it is probably quaternion product, of course. And what do I mean by this omega thing? Maybe I should also like give it some sort of operator, some sort of funny bracket type of thing, because the omegas cannot be just a vector. It must be a quaternion when it's subject to quaternion product, right? So what quaternion do you think that will be? It's sort of similar sort of story like here, right? I had the 3D vector omega, which gives me the axis of rotation, and I somehow need to lift it to a 3x3 matrix so I can realize this product, right? The same story happens here, except that I'm of course not lifting it to a matrix, but to a quaternion, right? So how do you think I can make a quaternion from the vector? In the same way as we were doing it in the class before, basically this, okay, this is my funny operation, don't quote me on that. This is just saying this is omega xi, sorry. Excuse me. Omega z k. So the way I lift this to quaternion is by saying that I create a quaternion which has 0 real part. So the coordinates of the vector, they become the imaginary components of the quaternion. And then the quaternion multiplication essentially realizes the same thing as the matrix multiplication here. Okay. Any questions? There is one question you should have. What is this 1/2 doing there? Right? Where did that come from? You can get it from the math. If you are doing the differentiation, you will just get a factor of 1/2. But that's the funny thing about mathematics in general, right? You can be deriving, you can know the derivation perfectly, but what you really need to know is what is the what the heck does it mean, the 1/2 there, right? Does anybody have an idea? Yeah?
Does that have to do with the angle being twice as much in quaternions?
That's exactly right. Yeah. Remember when we talked about the manifold? So we draw the manifolds again. So this is my SO3 manifold, or I mean the slice of it, right? With just like an identity matrix here, and the manifold of unit quaternions. Let me call it like Q1, for example, and here is the quaternion 1. Then, as I said before, going around this manifold, one full circle, gives me a 360 degrees rotation, right? Going around this manifold, the manifold of unit quaternions, one whole loop, does this, does 2 full rotations, right? So that means that if I move here by a little bit, or let's see, if I move here by a little bit, that corresponds to moving here by twice as much, basically. The rotations here are twice as packed as here. That's the reason for this 1/2. Right. You can also see it from the quaternion formula, that the quaternion is cosine alpha half plus the axis times sinus sine alpha half, and that's this half which is responsible for that. Now let me also give you an intuition behind this multiplication. it's also good to have it's possible to have a geometric interpretation of what that means. So it doesn't matter if we are doing it on quaternions or on matrices. Both are groups, both are Lie groups, which have their Lie algebras. So the Lie algebra is sort of funny. Have you heard that before? Lie algebra thing? Have you heard it before? I think I discussed it in my linear algebra class. I don't want to torture you by that. The Lie algebra sounds fancy, but all that is a tangent space at the identity of the manifold. Right? So the manifold is some sort of curved something. And of course, at every single point, I have a tangent space to it. Right? That basically, if I compute the derivatives of the manifold, I will get a locally linear approximation. And if we are in the context of Lie groups, if this is a Lie group, then this thing is called Lie algebra. Doesn't matter so much what it's called. What matters is what does it do. So this would be the tangent spaces at identity. And here this thing basically says that if I'm not at identity, if I am at some rotation R, so if my current orientation, if my rigid body and the current orientation is described by a rotation matrix R, then the derivative of this rotation exists in this tangent space, right? Like take this drawing with a pinch of salt because it's a high dimensional thing, but the idea here that it's tangent to the manifold, right? That's what means differentiating it, right? And that's exactly what this formula captures. This formula says, first rotate to R, and then give me this omega thing. It's not a general omega thing, because I cannot go like here. I must stay on this linear subspace, or affine subspace. And that's exactly what this cross-product operator takes care of. So that's your Lie algebra crash course, essentially. Now on quaternions, exactly the same story, except that this R wouldn't be like here, it will be like here, because here it's more compressed. But the same logic applies there, right? The derivative of my quaternion lives on the tangent space, tangent at the current orientation represented by quaternion Q, unit quaternion. All right? So that's what we needed to know about rigid body kinematics, or about computing velocities of a moving rigid body. And now we can look to forces and torques. So force is sort of obvious. Force is the derivative of velocity, right? So there is nothing special about it. So if I have my point number I, then the acceleration of that point is the derivative of velocity, which by Newton's second law is proportional to the force, proportional with the mass of that point, mass mi. So force tells us the translational effect of acceleration. Maybe that doesn't make sense. The point, what I want to get to is torque, where torque is the rotational counterpart of force. So this is the linear translational effect of force. But if we are dealing with rigid bodies, so applying a force to a rigid body, imagine I have a rigid body and apply some force to it. The force not only translates it, but also rotates it, right? And the rotational effect of the force is captured by the concept of torque. Rotational counterpart of force. So how is torque defined? You probably know this if you had some basic physics class. So if this is my rigid body, here is the center of mass. Here is some point where I'm applying force. So let's say this is again my favorite point number I. So there is a point. This is my vector pi. So let's say we are now in world coordinates. Usually we will be doing most things in world coordinates. And I have some force acting on this point, force Fi. All of these things, of course, can depend on time. So I'm ignoring the t's. So this will generate some torque vector, which I will denote as tau I. And how is the torque computed? Do you remember the formula? Did you have some physics? This is like a basic physics thing. The formula for torque is again cross product. It's pi cross product fi. So the pi is the vector of the point, the coordinates of the point in the world space with respect to the center of mass where I am applying my force. Okay? And this has a beautiful interpretation. If I look at the magnitude of Ti, by the magnitude of cross product, do you remember the formula? What is so this, right? The magnitude of cross product. What is the magnitude of cross product? So that would be the magnitude of pi times the magnitude of fi times something funny, the sine of the angle. And what angle are we talking about? Let me draw this again. So if I have my pi here, it's one vector, some force is acting on it like this, fi, then we are talking about the angle between the vectors pi and fi. So that's here, right? That's my theta I angle. And the magnitude of the torque is proportional to the sine of the angle. So when I will have maximum torque, when this is 90 degrees, right? When this force is exactly orthogonal to pi. That makes sense, right? If the force is exactly parallel to pi, then I will have zero torque, right? Because then I'm creating no rotation, right? If there is my point and my force pushes on it like this, then it gives this point the most incentive to rotate about this pivot, supposed to if I'm pulling like here. And if I'm pulling like here, I will be creating no rotation whatsoever. The torque will be zero. Okay. Now the length of the pi, I think it's called the moment arm or something like this. I'm not sure if I'm confusing with the Czech terminology. Anyway, the point is that the torque is also proportional to the length of pi, right? So what does it mean? It's best demonstrated with door. It means if the door is rotating about this axis, you are better off pushing on the door here than here, right? Here I need to push much bigger force than here. Right? Linearly proportional. Because this length is my pi length vector, right? So like try opening the door by pushing on this, right? You can do it, but it takes a lot of force, right? To generate the same torque, I need to apply much more force here than here. It's basic physics stuff. So let me draw it here for the record. If I have door and I apply force here, then I will certainly not generate as much torque as if I apply the exact same force further away, right? That's the principle of lever, right? If you can extend it even more, then you will be generating huge torque without really having to push too much. And the torques, you can sum them. So the total torque, tau, is simply the sum of individual torques over all particles, which means the sum of the pi's times the forces acting on all the particles. Why do we care about this? Is because we can be applying forces at different points of the rigid body. We can be pushing, like door is pretty good rigid body, right? I can be pushing at many locations of the rigid body. Okay, and now we are almost ready to formulate the equations of motion for a rigid body, except that we don't want to work directly with linear and angular velocities. It turns out it's better to work with momenta, specifically linear and angular momentum. So let's start with the easier one. That's the linear momentum. So what is a linear momentum? So for one particle, linear momentum is just mi vi. m is the mass of the particle, vi is the velocity of the particle, this is the momentum, right? So for the entire rigid body, I simply sum all of them together. It's called capital P, the linear momentum, P. The sum of mi, vi, where by vi I mean the velocity of an individual particle. So I guess I shouldn't really, well, okay, well, forgive me that. So the vi is the formula I have derived before. That's the formula for velocity of a point on a rigid body. Where is my formula? Where is my formula? This, right? Omega in world coordinates, cross product P plus velocity of the center of mass. So maybe I need to, let me give this like a little tilde, that it means the velocity of the particle. And here I have omega times the coordinate of the particle in world space plus v. But this v means the velocity of the center of mass, right? This is my center of mass, so this v is the velocity of the center of mass, and this v tilde was the velocity of the particle, right? This is the formula which we have derived before. That's the axis of rotation, cross product, the coordinate of the point. Oh, I should give it pi, right? Because this is capital P, this is lowercase p for the coordinate of the vertex. Is that clear? Do I need to explain the symbols again? That was no, you don't need to explain it again, or yes, it is clear. Okay, I need to move on if I want to finish this, which I do. So this is, I can just write it out, right, obviously. So this will be sum of miv plus this cross product is a linear operation, so I can as well pull it out, plus sum of mi pi. So this sum of miv, if my sum of mi's is capital M, the total mass of the rigid body, so this is mv, that's the, let me explain in a second what that is, and this is omega times, and this pi is the pi in the world coordinates, right? So this pi is equal to the rotation of p0 I, the object space coordinates of the point before I rotated it. So this is what? This is sum of mir p0 I. Again, I can pull the r out of it, so this is mv omega times r sum of mi p0 I. And this is what we said at the beginning, that we can choose the center of mass such that this is, we can choose the origin of the coordinate system in the object space such that this is 0, right? So this whole thing goes away. This is 0 multiplied by whatever gives me 0. So this is just mb. So this whole thing goes away, and the linear momentum is really just the sum. It's really just the velocity of the center of mass times the total mass of the rigid body. So the linear. So let me write it here. P, the total linear momentum of the rigid body, is the total mass times the velocity. I could give it back the t's if you want. The mass, you assume the mass is not changing unless you're like a rocket full of fuel or something like that, but usually or not. Usually it's a rigid body, a fixed mass. And this is the formula of the linear momentum of the rigid body. This was linear momentum of an individual point. And the good news is that the rotational components basically went away. They will be completely characterized by the angular momentum, which I'll explain in a second. Now the important relationship here is that the time derivative of p dot, is equal to the total force acting on the rigid body, meaning where the total force is nothing but the sum of the individual forces acting on individual points. This is Newton's law of motion for a rigid body. This is not as trivial as it seems, because to derive it, you need to take into account the internal forces between the individual particles, which take care of the fact that the rigid body maintains its shape, right? If they were just particles, they could go away. So this is not as trivial, but I will not do the derivations here. Okay, so so far we know how to capture the translational effect of the force. Okay. The next thing we need is the fun part. Guess what is coming? Anybody guessed it? Angular momentum. So I guess I could have said here that so far we need some sort of state variable for the rigid body. So the rigid body will be characterized by position of the center of mass, the current rotation, and we will say that the linear momentum, the PT, is also a variable, and we also need something to characterize the angular component of the motion. And what we will use, we will not use angular velocity, but instead we will use angular momentum. Why is it better to use angular momentum than angular velocity? Does somebody have an idea? It's a little bit tricky. The thing is that linear and angular momentum, they are conserved in nature. If I have some system of rigid bodies or particles or whatever, and there are no external forces acting on it, then linear and angular momenta are conserved. That's a law of nature. Velocities themselves are not conserved. There are funny cases when you have just a single rigid body. Imagine a rigid body with no forces in vacuum in space somewhere far away from anything. And if you spin the rigid body, it will have a constant angular momentum, but the instantaneous axis of rotation might be moving. Those are sort of funny effects related to like gyroscopic effects, the precession type of things. Like, you know, if you take a gyroscope, it does funny motions, which essentially are changes of instantaneous axis of rotation. And that's about as deep as I want to go into this. It's very cool, and if you study like physics and kinematics, this is studied in detail, but you need like several lectures to give this justice. All we care about here in PhysSpace is that the good variable to put into the state vector here to complement the linear momentum is the angular momentum, because it's conserved. So what is the angular momentum is denoted as L, capital L, and its relationship to angular velocity is given by this formula, I t omega t. So this I is not an identity matrix, don't be confused by this silly notation. I did not come up with this. This is, do you know what it is? Inertia tensor, exactly. Which tensor in this case means just a 3x3 matrix. And because this omega is in world coordinates, this inertia tensor is also in world coordinates, right? Never like mix apples and, or no, this is more like mixing something more weird. Don't ever mix the body space coordinates with the world space coordinates. That way we'll get weird bugs. So how is the inertia tensor defined for a rigid body? So again, if I assume that my rigid body is a collection of particles, then the inertia tensor is a sum of these terms. So this would be pi y squared, pi z squared, minus mi pi x pi y, minus mi pi x pi z, minus mi pi x pi y. Here is, what is here? Mi pi x squared plus pi z squared. What is here? Minus mi pi y pi z pi x pi z minus pi z pi y. And here is mi pi x squared pi y squared like this. So like I could also write the sums here, but that would make it even more messy. Where this pi, the pi is the pix, piy, piz, and the pi is nothing but rotated p0i, where this was in the body coordinates. This r is the current rotation of the body, so this is the vector rotated to the current orientation of the body. So because this is the world space inertia tensor. World space, we noted here. Okay. We need a way to relate the body space and the world space inertia tensor, because you certainly don't want to be computing this every time the object moves, because it moves all the time. So there's another way how you can write this formula using some funny, not that funny really, just basic matrix operation. So you can write this, if this is my pi vector, this guy, pi identity minus pi transpose. So what does this mean? This means this is the outer product. This is a 3 by 1 by times 1 by 3 matrix, so that creates a 3 by 3 matrix. This is inner product, so this creates a scalar. And if you just work it out, it's sort of easy to see that this is really the same thing as this. Okay. Now I know that the pi is related to the body space p0i using the current rotation r, right? You know what, let me drop this t's, otherwise I would have to put a t here as well, and t everywhere, so it'll be t's all over the place. So let's just remember that everything but the body space coordinates and the masses depend on time. They change in time. Everything, almost everything changes in time. So let me plug this form in here. This is how we get the relationship to the body space inertia tensor. So here I will get what? I will get there. So I will get p0i transpose r transpose r p0i, right? That's if I plug this in here, minus, and I do the same thing here, r p0i p0i transpose r transpose. Okay. Now RTR is good. RTR is identity, right? So this whole thing is equivalent to p0 I transpose p0 I times identity, because this is just a scalar. And this identity I can again write as RTR. Why not, right? And why yes? Because this way I can write the entire thing like this. R times sum of I, and now p0i transpose p0i identity minus p0i p0, that's the outer product here. And I must not forget to put RT here. Okay, everybody okay with this step? I pull this RT because the R is the same for all the particles, does not depend on the index I, right? This is all indexed over I. So you can take it out. And I have freed up this thing. And what do you think this thing is? Looks suspiciously similar to this, right? Except that here I have the P0, so this is nothing but the body space inertia tensor. So this is also inertia tensor, but this time in the body space coordinates. And so that means that's constant, right? Because the body space coordinates are not changing. The body is moving, but that only means that the rotation and the translation of the center of mass are moving, but the coordinates in the body space are of course fixed. So this gives me the relationship that the inertia tensor at time t is, let me put now back the t's, because the I body does not depend on time, but everything else does. And what I will need also is the inverse of the inertia tensor. So you know how to invert this, right? That inverting this is equivalent to doing this inverse RT transpose. Yeah?
Why are you able to take out the R and the RT when like the first term has them at the end of the...
This guy here?
Yeah, like how does that become the R and the RT split up?
Oh, because this is a scalar. Right?
Yeah.
That means that this RT I can pull on one side, this other. So because if you put this back, this will give you, this is just a scalar, this is identity, this will create RRT, right? It works. Yeah, I know it's a little funny, but it is true. Yeah, thank you. Okay, so this is how we can compute the inertia tensor from the body space inertia tensor, and that's how you do it in practice. You pre-compute the body space inertia tensor, and then you compute the world space using this formula. Oh, this is interesting that you can see it's exactly the same thing. I didn't realize this before, I only realize it now when I see that here. It's exactly the same relationship as the body space angular velocity and the world space angular velocity, right? Again, the R and RT essentially does the trick. Okay, and the last piece of information we need to know, and you have to trust me on that because again, deriving it properly takes some care. This is when you have Newton-Euler equations for the rigid body, this is the Euler's part. This is for the rotational motion, and that tells us that the derivative of the angular momentum, the time derivative of the angular momentum, is exactly equal to the sum of all torques acting on the body. So that completes the picture that tells us the whole story, how a rigid body moves subject to external forces acting on it. So let me summarize that. So our state associated with the rigid body. So you remember we had a state for, what was a state for a particle when we are doing particle systems? The state of a particle was position and velocity, right? X and v, right? So for a rigid body, we have the translational components, the position of the center of mass. Then we have the rotational component, that's the current orientation of the rigid body. Then we have the linear momentum, remember it was called P, and the angular momentum L. Okay, and that's our state vector. And now the laws of motion, basically for a rigid body, they tell me what is the derivative of the state vector. That means the derivative of all the components, right? Derivative of x, r, p, and l. And from what we have established before, the derivative of this is the velocity of the center of mass. The derivative of R is the formula I have derived before. That's the cross product matrix and the current orientation. The derivative of P, that's the Newton's contribution. That's the F, and this is the Euler's piece. That's the sum of torques. Where, of course, that this F time t means the sum of all the forces acting on all the particles, and the tau is also the sum of torques. I think I wrote this before, can't hurt to repeat that, on all the particles. By the way, the particles here are like imaginary, right? This is not like particle system where you would actually represent your particles in memory. Here is just like something we used to think about. You can think about, if I apply force at some point on the body, you can imagine there was a particle, right? But we never have these particles explicitly represented. We don't have like a data structure. You don't store them in memory. No. All you store is this state vector, and you store the body space inertia tensor. So how do we actually compute these things? So we already know how to compute the external forces and external torques, right? That's just somebody needs to tell us what forces are acting on the rigid body. That's what is causing the motion, right? The simple thing, there can be gravity, but you can be poking the rigid body. And when the rigid bodies will be colliding or contacting, there will be forces or impacts due to collision and contact. So this is what we will cover in the next lecture. So what about the V thing? So the V, the velocity of the center of mass, that we compute easily from the P, because there is the relation. This is the linear momentum of the rigid body, which is related to the linear velocity like this. Now the angular velocity we can compute from this formula. So the angular velocity, that's what we need here. The angular velocity is equal to the inverse inertia tensor times the angular momentum. And we know that the inverse inertia tensor is this, right? That's the RT I body inverse, which you can pre-compute, the inverse, of course, RT transpose LT. Yes. And using this, you are good to go and implement a rigid body simulation, simulation of a single rigid body subject to external forces. So this will already be taking care of all these funny precession effects and so on. You can code it up. It could be sort of fun thing to do. Some of you guys are doing this for your final project, so this is, I think, the right way to get that started. All you need to do is plug it into your favorite integrator, whatever you like, right? Because you know what the derivative is, then solving the motion is just solving the corresponding ODE. Now, after you actually try this, you will run into one problem. What problem do you think you will run into? If you do it all correctly. The problem is what is called sometimes numerical drift, because the numerical integration always has errors, right? And in this case, the errors will mean that your rotation matrix, RT, will, after a little bit of simulation, will stop being a rotation matrix, right? The rotation matrix needs to be from SO3, so it means this needs to be true. But after you simulate it for a little bit, you will find out that this is not quite true. That is not exactly identity. That the rotation matrix drifted from being orthonormal a little bit. So what do you need to do to fix that is to basically take away the deformation components which were introduced by an error, by a numerical error of the integrator. So if you are working with rotation matrices, how can we do that? How can we project it back onto rotation matrix? I think I discussed this already quite a few times here. So the problem here is R is not a perfect rotation anymore. That's due to errors, numerical errors of the integrator, because we are working only with discretized time, right? Actually, it's sort of nice to think about it on these manifolds, right? If you take infinitely small step, you essentially stay on the manifold. But if you take some finite step, you sort of go away from that manifold a little bit, right? So what you need to do after going away, you need to project it back on the manifold, right? So how can we do that with rotation matrices? You should know that. We have a matrix which is sort of rotation matrix, but not perfectly, so we want to make a perfect rotation matrix out of it. You could do that. The problem is that would not really be orthogonal projection, right? This could mean that you like take something and project it onto something like this. If you want to do orthogonal projection, then the right way to do it is using polar decomposition. So you compute polar decomposition QS, where this is a perfect orthogonal matrix. This is a symmetric matrix, which you just discard, and therefore you orthogonalize the matrix. And why this works better is because this Q turns out to be the closest rotation matrix to R in terms of Frobenius norm. So this matrix minimizes this thing. And I don't have to go again saying that this Q can be computed from SVD. We have already done that before. The correct SVD, the SVD that gives you rotations. Now, computing a polar decomposition for every rigid body in your simulator is not ideal because it takes some time. The polar decomposition for 3x3 matrices requires some iterative algorithm. So that's another reason why people prefer to use quaternions for rigid body simulation. Because with quaternions, what this drift means, right? Here is just one extra coordinate, right? Quaternions have 4 coordinates, and this manifold Q1 has 3 degrees of freedom, right? So projecting a quaternion back onto the hypersphere of unit quaternions is extremely simple, right? How do you do it? If I give you a quaternion that's not unit, and I want to make a quaternion that is unit, that's just like normalizing a vector, right? So all you do is divide it by the length of the quaternion when you are looking at it as a 4D vector. As simple as that. Just compute the norm and divide by that. That gives you a unit quaternion. So this is your Q nu. That gives you a unit quaternion, which is a perfect rotation. Much easier to do than like worrying about polar decompositions, right? The other advantage is that in quaternions, to begin with, your state vector, let me write it here. Your state vector would be xt, that's the same. Here you would have the quaternion, qt, and here it's also the same, the linear momentum pt and the angular momentum lt. Now this qt is only 4 numbers, as opposed to 9 numbers you need it for a matrix, so you need less memory to store that. That's another advantage. And these reasons together mean that people usually use quaternions to represent orientation of a rigid body in a simulator. Now the one piece we need is to compute the derivative, but I already told you how to do that. For most pieces, for most parts it's the same. This is just the velocity, right? And this is the formula I showed you before. This is the 1/2. That's the funny part. Omega t qt. And this is, of course, the forces and the total torque. So the only difference is here. This is the formula we had before. I have shown you. I didn't really derive it, but the derivation would be the same. You would just differentiate the quaternion rotation. Where did I have it? Somewhere around here. Oh yeah, here. This was this formula here. So that's what we can use here to replace the rotation matrices with quaternions. And the whole thing works just like before. The only piece is that when you are computing the axis of rotation, the omega, then you need the rotation matrix, RT, I body inverse RT transpose LT. So to compute this omega, what you need to do is convert this quaternion to a rotation matrix, right? But it's a very simple conversion. I showed you before how to convert quaternion to a rigid transformation. So that's what you do. You compute this, you have your omega, and the rest is the same. So that's the recommended strategy for simulating rigid bodies, to use the quaternion representation due to these advantages. Okay, so this is basically it. This is the unconstrained motion for rigid bodies. And next time we will cover what to do when the rigid bodies are colliding and contacting with one another. Any questions? All right, so I will see you on Monday, and we will finish this off with the collisions and contacts for rigid bodies. All right.